And our next speaker is Mario Gracello from the University of Palermo.
Hi. Okay, thank you very much. Let me see how this works, or is my presentation? Okay, so thanks a lot for having me here today. The focus on my talk is, again, photo evaporation, but this time I will try to focus what I'm going to say about clusters. We saw at the beginning of this session that the amazing things that we can do when we study the nearby evaporating disks at a high spatial resolution and spectroscopy, all the very important lessons that we can learn. Well, I don't think to stop here now. But what I want to really focus on this talk is actually what we can do when we analyze photo evaporation ongoing in star clusters, starting from intermediate massive clusters, let's say with a mass between 10 to 3, 10 to 4 solar masses, where we actually have the possibility to understand how photo evaporation can impact a global population of stars with disks that born in one of these clusters. These clusters typically host a rich population of massive stars, which are typically concentrated in their core. And one of the things that we can do, one of the things, not the best thing or the only thing that we can do, one of the things that we can do is just to select all the stars associated with the cluster, select those that have a disk, those that don't have a disk, and see how the fraction of the stars with disk actually changes across the field, across the cluster, across the different environment that the cluster can offer. A lot of people have done this in different clusters, like SIMSOB2, 6611, 2244, and so on. And what people typically observe in this cluster is that the fraction of stars with disk tends to decline when you go to the center, to the core of the cluster, and most of the massive stars actually are. Now, let me point it out that I also, in one case, more massive case, which is SIMSOB2, we actually observed this very nice smooth decline of the disk fraction when you go from the outskirt of the cluster toward the center. Now, of course, this can be mimicked by several other effects. So people must be very careful in interpreting this kind of results. There are different other effects that can result in this kind of spatial distribution. And there are also authors, like, for instance, the papers which are related to the MISTIC survey that actually question these results on this class of stellar clusters. But let's go on. Let's go further, because now we have instrumentations like JWST, like MUSE, wonderful instruments that actually allow us to study the global population of stars with disks in the superstar clusters, which are clustered more massive than 10 to 4 solar masses. Typically, they are hidden behind very large extinctions. They are very distant to us, but they're incredibly interesting because for several reasons. First, because they host the most massive population of stars that we know in the Milky Way. Then, because they are the typical star-forming environments in galaxies which are experiencing intense epochs of star formation, and also because together with photo evaporation, we need to account for close encounters. We need to account also for the presence of relativistic particles, as I will try to convince you later. Let's start from this wonderful result by Winter and collaborators. I think that I showed this plot more than Winter itself in these years. What they've done was to study a bunch of very massive clusters and calculating these clusters the typical FUV flux, different radii, for the typical stellar density. They put these numbers in their models and then found out that for all those clusters which are well above the blue line and all those that are right toward the red line, photo evaporation and close encounters can disperse protoplanetary disks in less than 3 million of years. So, and as you can see, there is a bunch of clusters which are well above the blue lines at all of the distance from the cluster center. Now, does this mean that these disks cannot form planets? Now, a few years ago, I would have said that actually this may be true. But then I decided to study a bit, and I realized that there are a lot of people that have done simulations of planet formation in evaporating disks, or disks which are in a very energetic environment, and actually there is still the chance to form planets. Even when the dust-to-gas relation is affected by the surrounding environment, if the disk is forming planets quick enough, and they typically form rocky planets, which is something actually quite intuitive, even in this kind of environment, it's a very energetic environment, you can still form planets, which makes the things even more interesting from one point of view. One ingredient that we must account is the fact that in superstar clusters are the only environment in which we have to take care also for the presence of intense flux of energetic particles. When you observe Western 1, Western 2, WU3, Sinus Habitu in gamma rays, you see that they are very bright in gamma rays, and this is because they are producing energetic particles, okay? They are producing energetic particles in termination shock of the cluster, they're producing energetic particles in the winds of the massive stars, and this is an ingredient that can impact the evolution of disks, that can impact the planet formation process, and also the early evolution of planets, and even the habitable zone, that one. Following other orders, okay? Now, what we are doing in the EVOX cluster is focusing our attention on Western 1 and Western 2, just because they are the best targets in which we can do this kind of analysis. They are very massive. Western 1 is the most massive cluster that we know in the Milky Way. They are quite nearby. They are quite young, in particular Western 2, so they're hosting the richest population of massive stars that we know. So they really have all the ingredients we need to actually analyze these kind of environmental effects on the global population of stars with disk. Now, this should be the point in which I should show you amazing results. Unfortunately, it's too early for us, so I will just show some nice pictures. Sorry for that. But they are very nice. I mean, starting from NIRCam, this is the NIRCam image of Western 1, and as you can see how the cluster really pop up in a wonderful way in this image, even with some nebulosity, but I will come back to this later. But not only nice images, 2 minutes, not only nice images, but also nice photometric data. We have a bunch of diagrams called Cole and Cole-Mack diagrams. I'll show you one example here. The blue, can you see the blue? There are the blue dots, which are NIRCam sources with an X-ray counterpart, which are mainly cluster members. And from this diagram, of course, we will do a lot of things. And one of these things will be to try to select the disk population of the cluster and see if in this kind of cluster, actually, you can find stars with disk and where you can find them. So this will be very, very interesting in the next month, for the next EAS. This is also the MIRI image of Western 1, which is even more shocking. We were shocked when we saw this image for the first time, because we were not expecting all this very complex and astonishing and structured nebulosity all around the cluster. The cluster core is in the center of the image. And this is really indicating that there is in this kind of cluster overall global feedback produced by this incredible population of massive stars. It will be very intriguing to see how the MIRI images, what the MIRI images will tell us about the population of stars with disks in Western 1. And of course Western 2, but we are still receiving the data. So for the next meeting. These are my conclusions. This talk is not meant to be conclusive. Of course, there is a lot of people doing an excellent job with JWST, with Muse in this year. You can see a bunch of programs that have been accepted in these 3 cycles. I didn't have time. I just had 8 minutes, so don't blame me if I didn't mention your works. Blame the organizer of the session that gave me all the 8 minutes. And I mean, I stop here, okay?